Hey guys, how's everything going? This is JSer. In this video, I'm going to take a look at LeetCode 692, top k frequent word. We're given an empty list of words, return the k most frequent elements. My answer should be sorted by frequency from the highest to lowest. If two words have the same frequency, then the word with the lower alphabetical order comes first. Well, this is pretty straightforward, right? We could just count them, right? Count each word and sort them. And sort them and get a top k, right? And this is a naive solution. Let's first try. Okay, which is the brute force solution with sort. So okay, what we gonna sort? Of course, we collect the unique words, right? First, we loop through all the words and get the count, and then find the unique words, and then sort them. Well, pretty clear. So use a map to track the count of each word. Use an array to push to the the unique words. And 3, sort the unique words first with count, and then with what? If the first and lower alphabetical order, lexical, and then lexical order. And then 4, slice the top k, right? Pretty straightforward. Let's do it. Okay, the first map is count map. We have a new map. And then comes the unique words. It's empty array. And then for each word of words, we count map. Okay. If count map password, count map update with 1 increment, right? Get word count map. Oh, here should be set. Get word +1. If it is not in the map, I'll say we set with count set word 1, right? This is the count. So now we finish the first step. Use a map to track the count. And then, oh, I forgot. I need to. If it has it, we update it. If not, we set it to 1. But also, we need to push into unique words. So this array will only hold the unique ones, right? Duplicated will be filtered out in this if clause. Okay, now the third step, we need to sort. Cool. So, well, we could use the built-in sort, which is sort. Word 1, word 2. If word 1, we need to get the top frequent. So word count map, okay? Count map, get word 1 is bigger than count. Okay, if it equal. Oh, it's better. Equal is a different thing. So count map get. Okay, I'll cache the variables because we have a 3 if clause. Count 1 equals count map get word 1. Count 2 equals count map get word 2. Okay, yeah. If count 1 is more than count 2, we should return -1, right? It means the count 1 should be further from the origin. So count 1 is bigger than count 2. Then of course we keep it closer count word 1 closer to the origin. If they are the same, we will return word 1 smaller than 2. Oh no. We should be. I think there's a method called string local compare, right? I'm not sure. Local. What is that? Total local compare. Yeah, this one. Compare A, B. It should be -1. Locale compare. Locale compare. What is locale compare? What is that? String compare? I don't know. String compare? There's a compare thing. Oh, I forgot. Okay, I forgot. Anyway, because there are words, I'll say if word 1 smaller than word 2, return -1. Okay, if equals, okay, return 0. Else if word 1 smaller than word 2. I forgot the method. Okay, and then well, it's a little verbals, but anyway, I'll just at last I will return the unique words slice 0.k. Yeah, I think this should be okay. Let's try run the code. Yeah, it should work. Cool. We're accepted. Well, this is a brute force. Let's try to analyze our solution. First, we use a map. For worst case, suppose there is n words, okay? Wow, this is linear, right? Space. This is linear space. But this is still linear space. Then it was linear. And then this sort. Sort is gonna take O n log n, right? N log n. Okay, and this is a constant time, const, and then we slice. This is what we take. Okay, well, you see, the largest one would be O n log n, right? O n log n. So this is the time, space. Well, linear. So could we improve it? Actually, I think we could. I think we could improve it because I think we've done like a special case of k equals 2. I did this a lot. So for if k equals 2, rather than we unique words get the top, sort everything. Actually, for k equals 2, we don't need to sort all of the words, right? We just need to count the top 2. If it gets all the count, it's like this, and then we could use like create a top 2, right? We create a top 2. Yeah, we create a top 2, and then this is the top 1, top 2, and for each number, for each word, we get and compare it to this top 1 and compare top 2, right? And then if it is bigger than top 1, we insert it, we remove top 2. If it is in the middle, we remove top 2. If it is smaller than top 2, then we don't do nothing. So the array will be kept for only the length of k. So and for that, we can remove this log n, right? We don't need to sort everything. We actually use if we do that, the time here will be log OK, linear for k. So we could improve the time complexity from O log n to big O n, right? Big A here. We can remove the sort here. Wow. Isn't this great? Cool. So how could we solve it? If for 2, we can use a 2-element array, but for k, so here is the data structure of priority queue. For top k, The idea is very simple actually. The idea is, for suppose we have an array, right? Suppose we have an array, but we don't know how it is ordered. Like we have a top k, like some array. What we want is actually, if we found a word is bigger than the bigger than the smallest, and then we could just insert it, right? Remove the smallest. So if we found a word should be put it in. We need to sort it. Man, predicate doesn't work. But still, we need to sort. Highest to lowest. Okay, this is not predicate. Yeah, so we need to get the order. Wait a minute. We still need to do predicate. Okay, so this thing actually will hold the top k elements. Suppose we have found a word, we put it in, we push it, and pop the smallest, right? And we keep the length of k, right? If it is smaller than k, we just push, and when k words is in it, and then we every time we push one, remove one. Keep the amount to k, and then finally we sort. So actually we still need sort, but we could improve it to a k log k. We only need to sort. We only need to sort the k elements rather than n, right? So we actually improved a lot. Do we need the priority queue, or we could just keep track of the minimum or top two, top k, the boundaries, like say max and the minimum? If we do that, actually, if we do just naive array, we need to sort every time actually. So right, if like it's like A, B, C. Now, if I have D put in, we actually can track the max and the minimum. But after we push D, we don't know the minimum. What the minimum is, right? We don't know the minimum is. So if we already sorted it will be okay. We just insert it insert this one into the right position, right? Okay. So that will actually cost us like O log k. If we search, we could do binary search the. Okay. If we do this, actually we could use binary search and find it by log k. Find the insert position and remove the last one. And yeah, so this actually cost us O log k for every word, and then it will be n, right? N log k. And we don't need to sort for last one. Well, so this is actually cool. But if we use priority queue, we push each element in, we still actually need the linear time, actually. We need actually log n. It's still the log n, it doesn't change. So I think we'd better just keep it, not use priority queue, but use array to keep track of it, right? Yeah, so, wait a minute. Oh yeah. But for the implementation, if you use array, we need to do the search and insert it and insert it and remove the last one. It's kind of like difficult, right? If you need to write the binary search here and the sort everywhere. I suggest that we first use priority queue because the time complexity doesn't change here. This is O log k. For priority queue, we still need log k for the insertion. And yeah, this doesn't change, except that for priority queue we need to sort for last time, but that costs us n. No, it's cost us k log k. It should be, I think it should be the same, right? Like this is largest, so this will be ignored. So okay, for simplicity, we use priority queue here. So where is the priority queue? Please search on my channel. I think I just recently I've recorded a video about how to implement priority queue in JavaScript. It is a lot. It is very interesting. Please take a look. So here I will just copy my solution. Where is it? I think it should be like top. What is? First, allow me to search my priority queue. Priority queue. It should be. It should be top Facebook question. Okay, where is the priority queue? Is something case largest element? Something about K, I remember. This one, right? K closest points to origin. Oh, yeah, I found it. Priority queue. Okay, so this is the implementation. There's another video explaining this. Please search my channel for priority queue implemented priority queue in JavaScript. I'll just use this one in my top K frequent words. Okay, I copy it. This is a class for priority queue. Is pretty long. I don't expect someone to write this in a real interview. Okay, I'll use a. Okay, this is the queue equals new priority queue. Oh, this is another step. So first, I still need to count the map. But now we don't need the wait a minute. After we count it, we need to loop through the count map. So we don't need the unique words actually. Okay, we get the map, and then then what we do, we will create a priority queue to get top K elements. Okay, so each time we insert something, we need to actually remove the smallest one, right? So we keep the smallest one to closer to the origin. We create a priority queue, new priority queue. For this one, it will accept new priority queue. The naming, right? Okay, the naming. How we compare the words, right? This is the word 1, word 2. Well, plenty. It should be about the. Okay, it should be about the. First about the count, and then about the order, right? So it's the same actually. Okay, I'll copy the code here. Yes, this one. Okay, count 1 equals count market with 1. If it is smaller than it, then it should be further, right? If it is bigger than it, it should be closer. If it is equal to it, and then if it is equal to it, we return 0. I'm not sure whether our implementation support is 0. 0 means do not change, right? Okay, 0 is cool. If smaller with it should be closer. I think you should be alright. And then what we do, we will loop through all the words and generate this priority queue. Okay, I'll say for let word of count map, and this is the count. So now the smallest one will be the first element, right? Pole. Actually, for our this naive implementation, we cannot get the top. So I'll create a method called pick return this items 1. Const smallest root root equals pick. This is the smallest word, right, with the least count. Now we compare it with the count. So if count map count root count equals count map get for a undefined. Oh, theirs might be undefined. This undefined get undefined is still it's undefined, right? It's root. Okay, it might be undefined. So if it is undefined, which means we will add the element, right? Add word. If it is not, we only add it when when the amount equals to the minimum, right? So else if or it is not undefined, but I just use if, makes clearer. If count is bigger or equal to root count. No. Or if is bigger than root count, or count equals to root count. But the word is smaller than root. Yeah, so that for that case, it should be replacing the root, right? So then we should also add the word. Now, if the PQ, like the size, what is the size? We can change it together. So PQ size is bigger than K. If it's bigger than K, then we will do what? PQ poll. Remove the list one, right? So now we will have actually a prior queue with the K element with the exact word. But it's not perfect. Actually, the order is not kept. So we need to sort once more. Well, it's pretty. How can I say? It's not that cool actually. Yeah. So constant result would be the PQ items slice 1. Now here it's already not cool, right? Slice items slice from 1. Okay. And now we result will be used to sort. Anyway, so this is a problem for me to practice the product queue. Return the result. Is this okay? This really, I don't think it passed. Of course, we got a problem. We have, let's log the word here. Log the word count. We got I. The count is all right. So here's the problem. The root pick. We check the root count. versus the count. Undefined, we add, and then add. If the add is a PQ size is bigger than k, let's log the add method. Console log add element. Add I, and then no more adding. What? Count equals it, and word smaller than root. This is word, this is root. This is word, this is root. Ah, I see what the problem is. We should anyway, we should push it. Yeah, push it and then pull. Yeah, I made a super big mistake. There's no need to forbid the love here. Shit. So we could use or here. Count is bigger than root count. And then we could push it. And then if it is larger, I'll just pull. Cool. Looks great. I didn't expect it to be running. Let's say the case 4. Are we getting the right answer? No. Oh, why? So yeah. Ah, there's a there is a problem. Gosh. There's nothing about this actually. Shit. I'm sorry. Actually, we just put this into the priority queue, and if it is enough, actually this poll will just drag out the smallest, right? Yeah, I don't need to pick. I just add the word, and it's done. Actually, there's no need to compare. Nothing here. This should be the right thing. Yeah, you see. I'm a little stupid. Stupid boy. Okay, so this seems to be working. No. What? This size is not function. Uh-oh. Where did we use this size? I changed it to the getter. Still wrong? Using an other way where get size. Get size, no. Get size. Get size, no. Get size. This is size. No. This size. This size. Why we have coding? LeetCode. But we need to return I love. What? Huh? This is weird. So long. The add element. So we add I, we add love, we add LeetCode, and we pull. So we log the items, these items also. So we add I, and then love, and then LeetCode, and then love LeetCode coding. Why we have 3? When we push the LeetCode, we actually need to pull. We need poll, so let me block the poll. Poll result. Okay, add I, and then add love, and then add LeetCode. Why we we need to put actually LeetCode as 1, so we need to let's count. God, this is a problem. For product queue, we actually need to put this count with the smallest one to the top, because that is to remove, right? So count 1, if it's smaller than count 2, then it should be closer to the root. If it's bigger, it's farther, the same, and if it is smaller, then it should be left. So this one should be 1, this should be -1, and the sort here is right. Yeah, I made a super mistakes. I need to take more care on the constructor of product queue. Cool. I think we could get it past this time. Remove the console. Yeah, submit. Great, we're accepted. But not that fast. Let's try to analyze our time complexity here. This is for this one we use a priority queue. So here doesn't change the linear space. This is linear time for word traversal, and then this is the priority queue. The construct is empty, so it's okay. And now we get this linear, right? Okay, for now here's the problem. We add, this will actually be log k. Poll log k. Poll is still log k. And then we slice it. This one is gonna be slice. Okay, k. And the sort, wow, man, k log k. So finally the time complexity would be most determined by here, right? So yeah. So the time would be O(n) plus k times log k. Yeah, that's all. So it's actually, if n is much bigger, it's similar to like roughly to n log k, right? Yeah, space still linear time. The thing is that we use a priority queue, we need to sort that at last, right? But if we use directly, as I said before, if we use just a sorted array, might be like here. I just addressed here. If you use a sorted array of length k for insertion, here it actually will cost us log k. So this is O(n) log k, right? And still we don't need the last one. Don't need this one. Don't need the last sorting. So it will be better. Could be improved to this one. Improved to this. Wow, I think if we suppose there's a product queue, this is much easier to write. For the binary search, it's not that simple. Yeah. So that's all for this one. Hope it helps. See you next. Before we leave, let's see if there's a better solution of this problem. It seems that there's sorting first. Okay, as we did, sorting cost us n log n. Yeah. Heap is the priority queue. N log k. Heapify. At last, we need to sort, right? We got the hash map. Okay, priority queue. Yes, this is what we get. For it, we of the word. This is what the same. We get the list, and then we yeah. This guy is so clever. We don't need to sort it like this. This is dumb. I thought it was dumb. Sorry. Yeah. Super clever. Yeah. Yep. Actually, we don't need to this. This is the product key is already sorted. No. It's some kind of sorted. We just get the items. So let's see here. So it says, I'll just use a while loop the same. While PQ size is bigger than 0, what we do, we will push PQ pull. This pull will pull the smallest one, right? And then finally we return reverse. Wow, this is genius. I didn't thought of this. It's better. Yeah. So this code looks much cleaner, right? Much cleaner. And the time complexity here, this will be for all the, so this should be k, I think. There will be k elements, and the podet, and there will be, oh no, it should be the podet, and the rest must be reorganized, right? So it would be log k. So I think this still is k log k. Am I right? Okay, say time. We count. So each. This is right. Finally, we pop the kit as this is not in total. It says k smaller than n, right? Okay. So cool. So that's all for this one. So if the k is much bigger than it, actually the time could be, this could be set to constant. It's linear time, right? If you say something like this. So I'd prefer that we keep the nk in it. Okay, so that's all for this problem. Hope it helps. Product queue, very important, and it's often used in some top k problems. And yeah, just you don't need to write it by yourself. You just suppose the product queue is already there. We can directly use. And if you're interested in how product queue is implemented, how this code is written, I have another video. Please search on my channel. Please subscribe my channel. There will be more and more videos. Yeah, I'll see you next time. Bye bye.